Hello guys, welcome to another video. Today we work on topic 10, HL, multiple choice questions. So a little bit obscure topic, usually we have like many issues in this one. But anyway, let's see a couple of these problems and see the solutions of those. So number one, it says 4 identical positive point charges of magnitude Q are placed at the vertices of a square of side 2D. What is the electric potential produced at the center of the square by the 4 charges? So we try to find the electric potential here at the center. So this is the distance between every different particle. Let's call it distance r. So the potential, the electric potential is K times Q divided by R. So now first of all I need to figure it out how much is this R. This R, it can be given by Pythagoras theorem, of course, if you can imagine that this is a triangle. So this is the square root of d square plus d square, the two legs of the triangle. So this, of course, it gives you 2d square, so that d can go outside, and you have also the square root of 2. So this is your distance. So now you need to apply it here. So the electric potential, it's K times Q over the square root of 2, distance d times the square root of 2. And now this is the potential of one charge. Now you have 4 charges, so you need to multiply this. So the total potential, it's 4 times the individual potentials, so it's 4 times K times Q divided by d times square root of 2. And you see, of course, here you don't have any kind of this choice. You need to play a little bit with the numbers here. So let's multiply both sides, both the numerator and numerator with the square root of 2. Let's see what we can have. So you have 4 times square root of 2 times K times Q divided by d times 2. So from here, you can see that this will cancel out. It will give you the number 2, square root of 2 times K times Q divided by d. So of course, this is the correct answer, D. Number 2, it says that the diagram shows 5 gravitational equipotential lines. The gravitational potential on each line is indicated. So you see the numbers here. A point mass m is placed on the middle line and is then released. Values given in megajoules per kilograms. Which is correct about the direction of motion and the acceleration of the point mass. Now, as you see the equipotential lines, you can imagine, you can understand that actually here it's something very massive that creates this gravitational field inwards the center. So let's say it's a planet. So if you have another object away from the planet, what's going to happen? Of course, it's going to move to the left toward the center of the planet. So it can be either C, either D. And of course, here the acceleration of the object, it's going to be to the left as well, but it's going to be increase the acceleration. So either B, either D. Of course, correct answer here, it's D. Number 3, a moon of mass m orbits a planet of mass 100 m. The radius of the planet is r, and the distance between the centers of the planet and moon is 22r. What is the distance from the center of the planet at which the total gravitational potential has a maximum value? Now here, in order to understand this question, we need to create a graph. Now it's going to be a little bit hard to make it here, but I'll try. So here in the y-axis, it's going to be the gravitational potential of the planet, Vg. And here in the x-axis, of course, it's going to be the distance between the planets. Now you know that from the surface of the planet, this graph is moving in this way. So let's say here you have the maximum negative value and is decreasing like this. It's increasing actually with a relationship of negative minus 1 over r. Of course, here something different happens, but we don't have to care about that inside the radius, inside the planet, sorry. So anyway, so we care about this part. So you see that from that moment, from the surface of one planet and from the surface of the other planet, here is my relationship between the gravitational potential and the distance. So if you're looking for the maximum value is up here. Okay, because here it's negative, it becomes less negative, so we have the maximum value. And in order to find this, the total distance from here all the way to other center of the planet, it's 22r. So what I have to exclude 1r from here, I have to exclude something more from here, so the only choice here close to what I need is number C, so it's 20r. So number 4, it says that the diagram shows the electric field and the electric equipotential surfaces between two charged parallel plates. The potential difference between the plates is 200 volts. What is the work done in nanojoules by the electric field in moving a negative charge of magnitude 1 nanocoulombs from the position shown to x and to y? So here is your charge, you want to move it to the x and you want to move it to the y as well. So let's see first what is happening with the x. Now the change in electric potential, it's delta V E is equal to negative work done over the charge. So from here you need to solve for the work done. So it's going to be negative Q times delta VE. You have negative, the Q it's minus 1 nanocoulombs. We don't have to care about the units right now. And the change in the potential difference, it's from the potential of 150 volts minus to 100 volts, because of course it's the final minus the initial. So the work done here, it will be 50. So it can be either A, either C. Now what is happening to the Y? Well, because we move in the same equipotential line, so this one, there is no work done. So of course it is 0. It's either A, either B, of course it's A here for us. Number 5, a positive point charge is placed above a metal plate at 0 electric potential. Which diagram shows the pattern of electric field lines between the charge and the plate? So first of all, we know that the field lines on the surface, they always have to be perpendicular. So it cannot be A, it cannot be D. And also we see that we have a positive point charge, so the lines must be away from the charge. So of course, correct answer here is C. Now for the topic 10.2, the gravitational potential is V at distance r above the surface of a spherical planet of radius r and uniform density. What is the gravitational potential at distance 2r above the surface of the planet? So here we have a planet with a radius r, and at distance r, so actually 2r here, we have a potential V, gravitational potential. Now we're looking for distance at 2r away, so one more r, so this distance is total of 3r. So at this moment, at this position, we're looking for the new gravitational potential. So the first gravitational potential, what we have initial, the V is gm over the distance, it's 2r. Your new V, it's gm over the distance that it's 3r. So somehow I need to include this one here, so I'm going to multiply with 2 and I'm going to divide with 2 as well. So you see that you have 2 over 3 gm over 2r, so you have 2 over 3 v. So correct answer here is D. Number 2, the escape velocity for an object at the surface of the Earth is v escape. The diameter of the Moon is 4 times smaller than that of the Earth, and the mass of the Moon is 81 times smaller than that of the Earth. What is the escape velocity of the object on the Moon? So first of all, we need to work with the escape velocity, that it gives you the relationship between the mass and the radius, of course, of the objects. Now, we talk about the Earth here. Let's call it ME and RE. So the new V escape that you are looking for, it has some differences. The differences are that you have the mass to be 81 times smaller than the mass of the Earth, and the radius also to be 4 times smaller than the one of the Earth, so divided by 4. Now if your diameter is 4 times smaller, then the radius is 4 times smaller as well. So you need to solve this one, you need to create this relationship in here. So you have the square root of 2gme over re multiplied by 4 over 81. So you can take this one actually outside of the square root. It's 2 over 9 square root of 2gme over re. So this will give you 2 over 9 v escape. So correct answer here is D. Now number 3. A satellite in a circular orbit around the Earth needs to reduce its orbital radius. What is the work done by the satellite rocket engine and the change in kinetic energy resulting from this shift in orbital height? So what you have here you have a planet, here you have your satellite at this position orbiting at this radius, and what it needs to do, it needs to reduce its orbital radius, so it needs to go to a smaller one closer to the surface of the planet. Now let's see what is happening in each one individual. Let's talk about kinetic energy first. Kinetic energy, it's given by the orbital velocity of the satellite. So the v-orbit, the orbital velocity, is actually given by this formula, gm over r under the square root. Now here, what you want to do, you want to decrease your radius. From this high radius you go to a smaller one, so it's pretty obvious that the orbital is going to increase, so that means that your kinetic energy is going to increase as well. So it's either C, either A. Now the work done by the satellite rocket engine. Now since you go to a smaller radius, the change in energy it's negative. So the work done, it must be negative. So it's either C, either D. So of course, correct answer here is C. Now, in order to make it, to understand a little bit better, why we have negative work. If you have negative work, it means that you need to exert a force in the opposite direction of the motion. So as the satellite, it moves to a smaller radius, the force that you exert, it's in this direction, opposite to your motion. Because what you have to do is you have to slow down your motion in this lower orbit. Because if you go with a high speed, then it's not going to be, the speed is not going to be enough to create this circular path, it's going to go straight into the planet. So you see that the motion is in this direction, it moves to the left, but the force is in the opposite direction. Okay, because this is what we have to do, is to slow down the satellite as it moves towards to a smaller radius. So negative work done by the satellite rocket engine. Okay, be careful with that. So correct answer here is C. Number 4. It says that the satellite X is in orbit around the Earth. An identical satellite Y is in a higher orbit. What is the correct for the total energy and the kinetic energy of the satellite Y compared with satellite X? So something similar again. Let's see, for example, the kinetic energy of satellite X. Here is your planet. Here is your X orbiting in this path. Here is your Y in a higher orbit, orbiting in that path. So the v-orbit, as I said before, is the square root of gm over r. So here, the satellite X, it has a smaller radius than the satellite Y. So of course it has higher orbit. This is for the X. So higher velocity, higher kinetic energy. So it is either A, either B for the kinetic energy. Now let's see the total energy. The total energy is the kinetic energy plus the gravitational potential energy. And this is given by 1 over 2, the mass times the orbital velocity, I will call it V square, minus, because we have negative gravitational potential energy, gmm divided by r. So here I just want to fix a little bit this equation, and I see that this relationship actually it's the orbital velocity but square. So what I have here for the total energy is that I have 1 over 2 mv orbital square minus mass, the small m, times orbital velocity square. So if you do the math here, you see that the total energy is negative 1 over 2 mv square, so it is negative kinetic energy. And it makes sense because at infinity, your gravitational potential energy is 0. So your total energy, it will be the kinetic energy. So what we see from here, that the kinetic energy of satellite is bigger. So if you have the negative sign here, that means that the total energy is going to be smaller than the energy of y. So correct answer here is B. And now number 5, the escape speed from a planet of radius r is v escape. A satellite orbits the planet at a distance r from the surface of the planet. What is the orbital speed of the satellite? So here again, something very simple to do. We need to work with the escape speed, that is the square root of 2gm over r, and the orbital speed here is the square root of gm over 2r. So I need to include this relationship in here. So what I have, I can multiply up and down with number 2gm over 4r. So this is actually the square root of 2gm over r multiplied by 1 over 2. So it's the v escape over 2. So correct answer here is A. Okay, that's all for today, guys. A little bit difficult topic, this one, but we have to practice a lot. So study hard and good luck.